I think I'll go ahead and get started. I just want to welcome everyone to this month's seminar series meeting for Sigma Xi, the UAB chapter. Today, we have Professor Elias Parakis, who's been kind enough to join us. And I will introduce our speaker in just a minute. Just a few reminders. Thank you for your Sigma Xi membership. If you need to renew, you have the link there for the website. And please let us know. You can reach out to our email address on Gmail if you need help renewing or joining, or if you would like information about UAB Sigma Xi. Also, a reminder that we have the 2021 annual meeting and student research conference, which is a virtual meeting, November 4th to 7th, and you can check out that and get some more information with the link provided there. We would also love it if you would nominate requested or recommended seminar speakers. Nominations for membership, please reach out to us via email. And when you do so, please include your nomination for the seminar speaker with their contact info, a short summary of why you're nominating the speaker, and details of the nominee's professional background. Please stay connected with UAB Sigma Xi to get information about monthly seminars and events. You can, again, email us or like us on Facebook. We also have a YouTube channel where we upload speaker video. Thank you for attending the October monthly seminar for Sigma Xi. We have our speaker, Professor Elias Parakis today, who is the chair of the UAB Department of Physics, for his talk, A Quantum Leap into the Future of Work. So Dr. Parakis is a fellow of the Optical Society of America and has been recognized for contributions to many body theory of the coherent optical properties of semiconductors and metals. He received his PhD and master's degrees from the University of Illinois at Urbana-Champaign, and his diploma in electrical engineering from the National Technical University of Athens in Greece. After 4 years as a postdoc at AT&T Bell Labs and Rutgers University, and at Vanderbilt in 1995, and where he received the NSF Career Award and was honored with a Faculty Research Participation Award at Oak Ridge National Laboratory. In 2000, he was offered the opportunity to serve in his birthplace in the south of Greece as a professor at the University of Crete and the Foundation of Research and the Foundation for Research and Technology, Hellas, a premier research facility funded by the European Union. And then in 2005, he served in several leadership roles, including head of Department of Materials Science and Technology and as associate chair and director of undergraduate studies in the Department of Physics. So in 2015, he joined UAB as professor and chair, and he has a mandate to build internationally recognized student-centered 21st century Department of Physics that fosters excellence and innovation in research, education, and community engagement. And during his 7 years in the department so far, he's worked to expand the department's impact by synergistically combining targeted interdisciplinary research aligned with national U.S. initiatives on advanced material science, high performance computing, and photonics. So without further ado, I would like to hand it over to Professor Parakis for his talk. So thank you so much for joining us today for this talk on a quantum leap into the future of work. So I will stop sharing and let you share your slides.
Thank you very much, Lauren. So good morning to everybody. So let me, you can see, okay. All right, so in case you fall asleep during my talk, here are the main points that I would like to get across. Point number one is that repetitive work is taken over by computers and artificial intelligence. So we as humans need to do something that we cannot compete with machines, something that is our competitive advantage as humans. So there are 5 21st century skills that are of value to you for this. They're called problem solving, they're called critical, creative, and imaginative thinking, they're called collaboration, communication, and ethical reasoning and mindset. If you combine these skills with technical knowledge, you can solve society's grand challenge problems in science, technology, engineering, mathematics, and medicine. All right, so let's go into how to do that. So far, we have had 4 industrial revolutions. The first one in the late 1900, I mean, like the late 1800s or so, had to do with using water, steam engines, coming up with manufacturing eventually, creating the concept of a city. And there, to participate in the workforce, what you needed to do is physical labor. You would do apprentices. You would learn very specific things. The second revolution was around electricity and mass production, Ford cars, etc. That was in the early 1900s, let's say. And there were issues like productivity standards and specific skills that you would have to develop. The third revolution is around computers, automation, and then simple digitization. So there you would have to do digital literacy. That's like 1980s, 1990s or so, and still going on, of course. There you had to be digitally literate. You have to know specific things about using a computer and the internet. And it was a time where disciplines in STEM were in high growth. And the fourth industrial revolution is what we're experiencing today. This is based on artificial intelligence, machine learning, and quantum engineering lately. And there, digital literacy is not enough. You have to have digital fluency. Disciplines are not enough. You have to do transdisciplinary research. You have to develop the 21st century skills that I just talked about. You have to be adaptive. You have to be a lifelong learner. And the underlying theme of this century is probably going to be convergent science, meaning all the traditional disciplines will get together to solve some really big problems facing society that are insoluble problems, but also very critical for society. All right, so in order to participate in the fourth industrial revolution, we have to be in tune with the demands of the fourth industrial revolution, not the third, not the second, not the first. So the first thing we need to do is retire 3 questions. First question, what do you want to do when you grow up? Not a good question anymore. Second question, what is your major? Not a good question. And what do you do? Not a good question either. For the fourth industrial revolution, forget about the past, it was different. All right, so why is that? When do you want to, what do you want to be when you grow up? Well, 65% of the jobs that you will be doing do not exist. So you don't know how to answer that question. Furthermore, 47% of the jobs that exist today will be automated by 2033. So these are studies, that show this. So what is your major? Okay, you're going to do your major, but are you really going to work in your major? 27% of students graduating in a major work in that major going on. And then even if you do, maybe the work that you will be doing will be automated anyway, computers will take over. So you have to do something where you have a competitive advantage. What do you do? Well, how do you answer that question when on the average, people will change 17 jobs across 5 industries during their lifetime? So we have to adjust to this reality. And even if these studies are not correct, this is a trend, and definitely something out of this trend will be the reality. So this means that our entire way of going through our life has changed. So in the old economy, we had a lifespan of, let's say, 73 years or so. Then we spent the first part of our life educating ourselves. Then the second part of our life was around work. And then we would retire. So we would go in this non-monotonic way, following this bell curve through our life. So we would work more and more and educate more in the beginning, and then stop educating and then working, and then we retire. In this new economy, things have changed. So work is now engagement, education is learning, and forget about retirement, think about reconditioning. So the first part of your life, and also of course your lifespan is probably around 90 years now. So that's significantly longer than the past. So be prepared to be around much longer than you were before. So in the first part of your life, you will spend educating, of course, But then at a certain point, while you continue education, you will engage. So you will be doing internships, for example. And then you will go back to learning. And then you will engage again, and then you'll go back to learning. And at some point, you may need to take some time off and recondition yourself. And then you go off again, and so on and so forth. And the retirement comes very late. So this is a new way of going through your life based on realities that whether you like them or not, they're here. And the question is how we deal with this reality and how do we make it work? Because that's a highly non-trivial question. So you have to change the questions that you're asking. So don't start, what is going to be my major? What is going to be the job that I want to do? Start with the first question, what is your passion? So you want to go through 90 years of life on this planet, what it is that you would like to impact on this planet. How do you want to change the world? What is your passion? What do you feel really passionate about contributing in this planet? So start from that and say that I'm going to spend my life promoting these ideas. These are what are important for me. This is what I have a passion about. After you're done with this philosophical question, you have to get some skills, meaning you have to be productive and you have to actually, if you want to have an impact, you better have an impact, which means you have to have some skills that will allow you to have an impact. So you have to develop these skills. So you have to empower yourself to be able to fulfill your passion, your dreams, what it is that you want to have an impact with. And then you take these skills and you find a job, because you need to have a job, because otherwise you won't be able to either develop skills or serve your passion. You will be busy trying to stay alive. So that's not a good way of going through your life. So jobs are extremely important. But the question is, you're going to get a job and you may have to change the job in a few years. So then you go back to your passion. What it is that I really want to do. Let's remind myself. Do I need some more skills? Let's get these skills and then I'll find another job. And then later on, I see that my dream job is the job that I would like to do because that serves my passion. So for example, if I want to use a business example, think of Amazon. So Amazon was created in the early 1900s, right? So everybody thought, gee, there's this new bookstore. There's also Barnes and Noble, that's another bookstore. So which one will prevail? Or this is this toy shop. We also have eToys. That was the big online, like toy shop, right? We had Toys R Us, right? So why Amazon, right? It's surely going to go bankrupt. That's not how Amazon started. It started with this idea that it would be able to use the online medium to do business in a way that nobody was doing before. It didn't care about books or anything else. It just wanted to do business. And through its life, it all of a sudden became a big data company. This has nothing to do with books. Why? Because that mission that the company had was best served by developing big data. So it's something, so don't want to make the analogy too much, but this is kind of an example of how you think about your passion, your skills, and your jobs. All right, so how about physics? So in physics, these are the number of bachelor's degrees awarded in physics. And then this is the number of bachelor's degrees awarded in STEM as a function of time. So you see here around 2000, physics started going up dramatically. Other STEM disciplines had started earlier, meaning more, this is the number of degrees awarded in the country. So there's this big slope developing after 2000. And this is exactly when these new paradigms started to play a role, where physicists now, based on their passion and on their DNA as a scientist, are able to contribute now in jobs that are not associated with physics, which means we need more bachelor's degree because there are many, many more jobs that can be served by a physicist and their passion and how they want to impact life. So for example, physicists right now, 36% are engineers, 23% are computer scientists, 25% are non-STEM, including medicine, 30% switch to other STEM disciplines. Only 5% have jobs that can be called physics and astronomy. And this will change in the future. What will not change is physics. So at UAB, what we did is we followed evidence-based practices to change our program around this way of thinking, this mindset. And we got recognized as one of the top 25 programs in our accelerated combined physics bachelor's and master's degree that we started in 2020. So this is what we did to take action in this new reality and help our students be capable to serve their passions in this new economy. In terms of local jobs, there's this report commissioned by the city of Birmingham called Building IT Together. This was done by Burning Glass. Burning Glass is a consulting company across the country. And the conclusions and the question is, how will economic development happen in Alabama, right? Recall that Alabama is one of the poorest states in the country. I think it's probably 46, if I'm not mistaken, out of 50 states, let's say. So that's pretty poor, right? So how do we bring economic development in the state? Because remember, you may have a passion and you may have skills. If you don't have a job, you also need a job. So the Accelerate Alabama 2.0 economic development plan basically agrees with the Building IT report and are saying basically three things. These are the three industries that Birmingham and Alabama need to grow in order to create jobs. Advanced manufacturing, so in physics it's called advanced material science. Information technologies, in physics is called high performance computing, quantum computing, machine learning for condensed matter physics, and so on. And there's life and biomedical sciences. It's called in physics biomedical devices, or preparing students to become doctors in a way that they will be competitive doctors in the future. For example, issues like precision medicine, the future, is best served by physics. Again, for the reasons I discussed before. What is your passion? What are your skills? And you don't know what jobs will be in the future. So both of the Building IT Together plan and Accelerate Alabama note that employers, as we speak, are really seeking for candidates that have demonstrated their proficiency and ability to solve complex problems. You can learn Tableau or any other software easily. What you never learn, and you only learn right now in your bachelor's degree, if you choose properly to develop the proper skills, in other words, with the right choice of bachelor degree, is that you develop the ability to become a problem solver. So you use the traditional disciplines and software to do, for example, computational research. You become a computational scientist. So you develop these skills that will allow you to get the jobs and actually get the jobs done. So how does physics develop this? Through physics research, which is an ideal tool to develop 21st century skills, the 5 skills I mentioned in the beginning. First of all, you never become a physicist by watching a professor talk. Second, in physics and in research, you know where you want to go, but you have no clue how to get there. That's the definition of research. You know what you need to solve, what you need to explain, but you have no idea whether you're able to do it or not. If you are able to do it, then it's not a real research problem. It's not called research. It's called a project in your undergraduate degree. How do you get there? To be successful as a researcher, as a scientist, you must be a problem solver. You must work effectively in teams in the lab. You must have STEM content knowledge. You must be a self-directed learner. Don't expect your courses to teach you what you need to learn. You have to read papers yourself. And you have to make ethical decisions. If you're not ethical, you will fake data. It has happened many times. That's not good for society. It's not good for physics. It's not good for you. Now, research requires not just being able to program, but you have to be able to reason with the data. Data have to speak to you. you have to have imagination. You have to imagine how to solve the problem, not think. You have to imagine. And you have the ability to break down an insoluble problem into manageable parts. So a real research problem is hard. The problems that we can actually solve today are easy because you can do it. So this means that they're easy. So if you break a hard problem into small chunks that you can chew and tackle them one by one, then you will be successful in research. That's what you learn in physics lab. And finally, research trains physicists to tackle complex situations that they have not encountered before. So there are problems that are considered hard. Well, if you're an undergraduate in physics, you think that the problems in physics are really, really hard. If you're a researcher, you also tackle complex situations. All right, so this is how the lab looks like. These are like how the problems that you do in a physics department look like. They're called advanced materials, advanced manufacturing, lasers, optics and photonics, computation, machine learning, high performance computing, exascale computing tomorrow, data science. You use data science to actually do research. You get funding to do physics research with data science, with machine learning and high performance computing. And then you tackle problems, and these problems have to be interesting from a scientific point of view, because if they're not hard problems, you will not develop your skills. And at the same time, you won't get funding as well, because you only get funded for the problems that have not been solved. And somebody out there must have solved them if they were that easy. All right, so let's go back to physics and just think about your classes and the four revolutions. So the first revolution was about steam engines, and so on. It was about mechanics, classical mechanics. That was about the time where classical mechanics was developed as well, 1800s. So classical mechanics says that motion is described by the concept of a particle trajectory. This means that all you need to do is calculate the position and the velocity of a particle as a function of time. And then that velocity and position, once they develop, they will stay constant forever unless you have a force. So force is the way in which you interact with the environment. So in the factory, the way that you control the machine is through forces in the 1800s. So these forces cause acceleration, and Newton's law says that F equals mass times acceleration. So you use that equation and you use mathematics or computers nowadays to actually do simulations based on this equation. That's the first revolution. The second revolution was based on electricity. And about the same time, electricity was a field of physics called electromagnetism. And in order to be able to deal with this field of physics, you had to introduce a new concept. So trajectories were no longer enough and forces were not enough. You have to think in terms of fields, electric and magnetic fields. That was a new concept. And then people discovered that electric and magnetic fields seemed very, very different. It was the compass, and it was the electric current, or things attracting or repelling, charges attracting or repelling each other. And then people figured out that these electric and magnetic fields are responsible for the entire chemistry and biology. And then Maxwell wrote his equations based on the concept of symmetry. And to make them symmetric, he had to predict the existence of electromagnetic waves, which means that rather than trajectories, position and momentum and velocity, you describe electromagnetic waves by a function of space and time that has this sinusoidal form. And you introduce new quantities like the wavelength and the frequency of a wave that do not have any meaning for a classical trajectory, for a classical particle moving in a trajectory. There's no wavelength, there's no frequency. And then you figure out that at the end of the day, all these different phenomena like radio or microwaves or X-rays or gamma rays, etc., all of them are really one and the same thing, this sinusoidal function with a different value of F, the frequency or the wavelength. And there's this thing called the speed of light by which these electromagnetic fields propagate. Okay, and then came the third revolution. So the third revolution was about computers, but it was also about material science. And then materials are made out of atoms, and atoms are made out of the periodic table. And the periodic table shows this very systematic behavior as a function of protons in a nucleus that people could not figure out how things could be so systematic. So people were able to spot this systematic behavior in the properties, and they were able to construct a table, the Mendeleev table, out of this consistency, but they couldn't figure out what this was all about. So quantum mechanics was the answer to that with a simple quantum mechanical model that obeys quantum mechanics, you can explain all the properties in the periodic table, and then you can put these atoms together to create materials with new properties by using computation in a way that was not possible before the third revolution, that make computers very powerful. Remember, in the 1980s, we had the Commodore computer. You've never heard of it. And you wouldn't have heard about Windows back then because they didn't exist. So the power of a computer, what was called a computer was this big room with air conditioning that you could hand in a bunch of cards, and people would run the cards through this big machine that occupied the entire room and give you a result. And that power that you got, computational power, was about as much as a personal computer nowadays. Now, when you have enough power, computational power, in the late 90s, early 2000s, then you can actually do calculations based on quantum mechanics and produce actual results that allow you to understand materials. But then there's more. So you may have called about this Einstein, Podolski, Rosen paradox, and this concept that Einstein did not believe in quantum mechanics. That was not true. What Einstein said is, surely I'm very smart and I have discovered general relativity, which says that there are these local variables that determine what's happening. And surely there are hidden local variables in quantum mechanics as well that explain all these properties. And you don't need all this fancy formalism like a wave equation to explain these properties. All right, so what are the properties that you need to explain? Well, in the third industrial revolution, the properties were about materials, as I said, and chemistry. So matter is made out of particles that attract each other. They're called electrons and protons. Whether you're a biologist, a chemist, or a physicist, it's the same. If you have two attracting particles that attract each other, then they will just fall on top of each other and everything will collapse. There's no universe, there's no materials, there's nothing, there's no life. So something must counterbalance this attraction to achieve stability. And there's nothing in classical physics that can be used to explain this stability of matter. Why do we exist? Why is there life? No life in classical physics. So the answer, Feynman summarized the answer, it's little particles moving around in perpetual motion. That's what keeps us alive. But what is this perpetual motion? Well, it's coming from particle-wave duality. So as we said, a particle supposed to move in a trajectory. What is a trajectory? You have a velocity and a position. So the particle has a momentum, mass times the velocity, and it has an energy, it's kinetic energy. Well, it still has an energy and a momentum because you measure them. But this doesn't mean that it will follow a trajectory. It will follow a trajectory in what you can see. It doesn't mean that it will always follow a trajectory where you cannot look. So the assumption that you're making is, if I myself cannot see something, then this means it doesn't exist, right? So religion is based exactly on the opposite concept, that you don't see God, but you believe that God exists, right? So it doesn't mean that everything that we think and look at, but still we have to be able to prove what we're saying and not just imagine it. We have to imagine it first because we can't see it, but then we have to prove it as well. So how do we do that? In new ways, of course. So here, the concept is that a particle, the conjecture, the postulate, the paradigm, is that a particle must behave like a wave as well as a particle, meaning it has a frequency, which is given by its energy. And then you have to get the right units. I mean, energy has units of energy and frequency has units of inverse time. So to make the connection between the two, you need a new constant that will take you from one unit to the other. And that constant is called h bar. We'll come back to that. And also it has to have a wavelength because that's what waves do. And this wavelength is related to its momentum, again, through this same mysterious constant. So it is fair to say that a particle is a wave particle and not a particle. And that produced the concept, or the theorem rather, of Heisenberg, the Heisenberg uncertainty principle. That is a well-defined mathematical theorem coming from what we know about waves. So to prove Heisenberg uncertainty principle, we have to believe in waves. And to believe in waves, we have to prove that waves exist in a way that that proof may not be through our eyes, but it could be indirect. But we believe in our equipment and we will do it. Okay, so that was quantum mechanics. And then the fourth revolution is about machine learning, artificial intelligence, including quantum computation, and the concept of quantum engineering. So now quantum mechanics turned from the 1900s of these exotic quantum states that nevertheless produced important quantum technologies like the laser, the MRI, or the superconductivity or superconductors, levitating trains and all of that. But quantum engineering is something different. Quantum engineering, the way it's defined, is do quantum information applications, more generally. So that's a thing of the 2000s. And it's based on the concept of quantum entanglement. And it has reached industry, right? So now you have technologies in the industry commercialized, starting to be commercialized in quantum communication, for example. And of course, we have quantum computation that we will talk more about. So in recognition of all of that, Congress in 2018 voted the National Quantum Initiative Act, which means that it devoted about $1.6 billion for 10 years in order to develop this concept of quantum engineering, meaning go from this esoteric concept called quantum physics and the Einstein, Podolski, Rosen that people were debating about in conferences with words, just like in ancient Greece. Plato and Socrates didn't do any experiments, right? They just debated. That was an excellent debate because that led to many things in today's society. And the debates between Einstein and Bohr led to quantum engineering. So now let's make it into real devices. How do we do that? All right, so we talked about quantum computers and quantum information. So a computer works with bits. So a bit is a yes, one, or a no. It's two states. So if you put these states one after another in some logical way and you're able to change them, then you create a bit and a computer. Then you have a lot of bits together that create a computer, and you have transistors and all of that to act as switches to go from one bit to the other. In a qubit, the quantum bit, you can have any state represented by a circle, by a sphere of constant radius. So you have a vector, any position of your vector can be pointing in any direction along this sphere. Each direction this vector points to, you get a different state of the qubit. So the qubit doesn't have two states. It has an infinite number of states. And it's based on the notion that if I have a vector, then a vector I can expand in coordinates, right? A classical vector. We expand it in the x and the y axis. So if we do a similar thing, and the two axes are the yes and the no state of the classical bit, and we have a vector, we can write it in two components, the x and the y component. And then this looks like a wave if each of these states are wave-like. They're like a wave function instead of like a classical state. Then we have an interference of waves. So if we have two particles going on each other, they will just go off if they collide. If we have two waves falling on each other, then matter will start oscillating in new ways. And that is the phenomenon called interference, which is a well-defined phenomenon in classical electromagnetic theory. So a similar thing, if we can have particles behaving like waves, then they can interfere, meaning the one and the zero can fall on each other together and interfere. So that in a nutshell is the concept of the qubit. So how does this work out? So let's say you have a wall and you create a hole in this wall and you throw in classical particles, balls. Then they will go, some of them will bounce off, some will go through this hole. And then if you have a screen on the other side, the ones that go through will pretty much collect, concentrate, just opposite to the hole. So that would be a classical experiment of throwing a lot of balls on a hole. If this was a wave, let's start from an electromagnetic wave facing a hole in the wall, we have the phenomenon called diffraction, meaning you will see a pattern on the other side, which means you will have dark and less dark spots on the other side. And this is the concept of diffraction. If you do this with particles and you believe that a particle is a wave, then you should be able on the other side to see a pattern where the particles are not concentrated like this, but they have a concentration. I mean, you will see some particles going here, less particles going there, no particle will go in the middle. Some concept like this. And in order to be able to do that, you have to make the hole small enough, because we know from waves that this hole has to be of the order of the wavelength in order to see this phenomenon. In a particle, we said a moment ago that the wavelength is related to the momentum of the particle. And to get the right units, you needed this constant called h bar. So this, if you put in some numbers for the classical velocities of the particle in everyday life, this wavelength will be extremely small. So you wouldn't be able to create a hole that is so small to be comparable to the wavelength. That's why you never see it. But if you just assume that there's no reason why particles and waves are different things, just like we have waves, we've seen them, they're there, we've noticed them, and we have particles, they are there as well. Nothing tells you that the two are not one and the same. So this concept, this way of thinking, leads you to this phenomenon. Okay, now let's put two slits. So this would be your yes and no state of the qubit. And then you throw in a wave, a particle wave now, on this. So the particle can either go through slit 1, and that would be the yes state, or slit 2, that would be the no state. And some particles will go through one, and some particles will go through others. And the question is, does this going through is like just having two holes, two classical holes, and you have a bunch of particles here and a bunch of particles next to the other hole, and that's all that's going to happen? Or are you going to get a pattern that you cannot explain with this classical concept? So the idea of the qubit is that you will create this pattern in your computer, in the bit, coming from this interference. So you will see a peak in the number of particles right in the middle, not next to the two slits, not next to the two holes, right in the middle. And then you will see places where there will be no particles and places where you get some particles. So this interference pattern will look exactly as if it was a wave. To explain that, you have two waves, the yes and the no state. And it's a linear combination, just like waves interfere in classical electromagnetism. And this phenomenon in quantum mechanics, this phenomenon, the corresponding phenomenon for a quantum wave particle, if we believe again that particles are waves, is called quantum coherence. Now let's do another experiment that you cannot do with waves, but you can do with particles. So let's say that you put a cavity and the particle is an atom that's in an excited state. So before it goes through the hole, it has to go through this cavity. And the atom is in an excited state. Now, when it goes into the cavity, it undergoes a quantum leap, meaning an atom can emit radiation which is really a photon in this case, and then go into another state. So that's the quantum leap of Bohr and others to explain experimental data that could not be explained otherwise, that had to do with experiments with light and atoms. Light has always been important for quantum mechanics. There would be no quantum mechanics without light, because light has experiments doing light have been important for quantum mechanics. And similarly here, you create a cavity. So you have the atom, it goes back to the ground state, out of the excited state, and then it goes off through the hole. And there's a photon remaining in here, trapped inside the cavity. Or the atom can go through the other cavity, there will be another photon, and then it will go through. So you still have particles coming out from the holes, but now these particles will be de-excited, they will be in their ground state, whereas the incoming particles were in the excited states. And there are two photons trapped in here that you cannot measure. You cannot look inside the cavity. You cannot see what's inside the cavity. Now, if you believe this, this means that the particle will come out with some wave function, which will be the yes, or another wave function, which will be the no state. The difference here is that we have a composite system, as we call it. So these particles had a photon inside them, which they emitted, they left behind. So we have to include this second system, which is the photon, which is now separated from the particle. So if a particle comes out of slit 1, then the photon is in state 1. If the particle comes out from slit 2, then the photon is in state 2, meaning in the other cavity. So these are two separate photons. If you take the square of this, if you take the square of this wave function, you will get this pattern. If you take the square of this wave function and note that these two photons are different, then you just get a classical pattern, meaning the particles will again concentrate around the two slits. You lose the interference. But your entangled system, meaning the system, the composite system with the photons, was in a quantum state, which means now you can have certainty again, but in a quantum mechanical way. So this state is called entangled state, and the phenomenon is called quantum entanglement. And this state is called the Bell state, which, using this concept that I just naively described here, you can have all your qubits, all your bits being entangled together as one big composite system. So one bit will be the photon, the other bit will be the particle, and the two know about each other. They're correlated with each other, but they may be far apart. One of them is out the hole, one of them stays in here. But they're still correlated because one of them exists because of the other being initially in a quantum mechanical state. So if you take the square of this wave function, you just get two peaks located at the slits, you lose the interference, but you have a quantum mechanical phenomenon. If you use this quantum mechanical phenomenon, you can do quantum teleportation, meaning you can transport this coherent wave function like this over a distance without really measuring these two coefficients. Because if you try to measure these two coefficients, you will destroy the qubits and you go back to classical physics.
Dr.
So without going back.
You have 10 minutes.
Okay. So what are the jobs? So now there's a quantum industry based on this phenomenon. So the jobs, 95% are engineers, 86% are experimentalists, 57% are theorists, 43% are technicians, 33% are application researchers, 90% work in sales, 10% work in business development, and 10% work in technical support. This is a study done in 2020 based on existing companies that work in the nascent quantum industry. What are the degrees? What are the skills that these people had? They were PhD in physics, bachelor's in engineering, PhD in engineering, bachelor in physics, master's in physics, master's in engineering, PhD in computer science, bachelor in computer science, associate engineering, postdoc in physics, PhD in chemistry, master's in computer science, PhD in mathematics. So this is a distribution. So overwhelmingly, these companies hire PhDs in physics and bachelors in engineering, with a big percentage of bachelor and PhDs in engineering and physics. And these are the kind of jobs classified in this quantum industry. So again, this is a study that was done in 2020. So this means that your passion would be the what, right? The why. What do you want to do? You want to affect technology to be able to solve the big problems of tomorrow. And for that, you need new technologies. But quantum industry didn't exist before. So what is quantum industry? There are the mature technologies, the old quantum technologies, like lasers, the GPS, and the MRI. So these are mature technologies, but they're quantum. They're based on quantum mechanics. There are new quantum technologies that are already in the market, which are quantum cryptography, quantum simulations, and quantum sensors. And then there's quantum computing, which is decades to come, because we still are not there, but this may be coming. And then there's a number of technologies that support this industry. They're called optics, high precision lasers, detectors, and refrigeration. So these are data from McKinsey. So if you have these skills and you have a passion to solve problems that society could not solve before, then you can get a degree in these fields, because you will develop the skills to serve these industries. But these industries will change dramatically. Then you go back and get more skills with the new jobs that will emerge, but don't wait for these jobs to come. All right, so how do I know that H bar exists? To measure H bar, we choose an everyday quantum phenomenon, and physicists call the radiation emitted by a hot object the Blackbody radiation. What this means is that the spectral distribution, I mean, how much intensity you get for each wavelength, for each frequency out of a hot body, an object that has a temperature, only depends on the temperature and not on the nature of the body, of the object. So you will get electromagnetic radiation emitted because you heat an object. And this radiation will have a wavelength in the optical, in the visible. And this distribution, how much intensity per wavelength, has a peak, but it has a distribution that does not depend on the object, just on the temperature. So let's choose the sun as a hot object. It certainly emits radiation. So it's called thermal or blackbody radiation. So we have the energy per unit time, per unit surface, per unit wavelength, and it has this shape. Let's estimate this total radiation intensity and wavelength of the maximum intensity. So this shape, as we said, is what physicists call universal. It doesn't depend on the object. It has the same shape. So all we need to do is calculate the maximum and the total under this curve, which is this integral, the total intensity and this. So we can do that by doing dimensional analysis. And since I'm running out of time, I won't be able to do this in detail, but the talk will be available and you can work it out for yourself. What does this mean? Get the units right. So if I want something that has the units of intensity, this is units of energy per time, power, over surface, length squared. So all the units come from three basic quantities, like length, mass, or time. Think about it. So these three quantities don't have to be length, mass, or time. They can be anything. So here they can be temperature, they can be speed of light, and this H bar. So if you get the units right, then you see that this intensity must be proportional to the fourth power of temperature divided by the speed of light squared, and it has to have this constant H bar to the third. So you get this by just getting the units right. So this was discovered as the Stefan Boltzmann law, an empirical law that you can just get from getting the units right, but to get the units right, you have to invoke a new constant. Otherwise, the units don't work. And the maximum length is proportional to the inverse temperature, and that's called the Wien law. This was also discovered empirically, and again involves this magic constant H bar and the speed of light in this way. Again, get the units right. Get something with units of length constructed out of temperature and out of the speed of light. And since these are not enough to get the units, just put another quantity there and get the units right. All right, so the intensity then will be given by the maximum length. So this h bar, this mysterious constant, has to be the intensity times the fourth power of the maximum wavelength divided by the speed of light squared. So if we are to measure that, we have to take a hot object like the sun, measure the intensity coming out of the sun, measure the wavelength. We know the speed of light, and then we create this constant. So we can do that, and I run quickly with this. So we need the intensity emitted at the sun. So the intensity is energy, is power per unit surface. So integrate over the surface, multiply by the surface. So that's the power coming out from the sun. This power is not lost. It just goes into a bigger sphere until it reaches the Earth, which is distance r away. So the total power will be the same, and will be the intensity reaching the Earth times the surface of this sphere, so that energy is conserved. So all you have to do is measure the rate. If you want to get the intensity on the Earth, you know the intensity on the Earth. You want to get the intensity at the sun, you have to get the ratio between the distance between to the sun and the radius of the sun. So that you can measure. You raise your hands like this, pointing to the sun, and you see that there's this angle theta there. This angle theta will be the radius, the diameter of the sun divided by this distance from just simple geometry, 2r over r. And to calculate that angle, all you have to notice is that this is the angle. So this at the end of my hands is of the order of the centimeter, and the distance is of the order of meter. So the angle will be like centimeter over meter, 1 over 100. And this has to be equal to the radius, the diameter of the sun divided by the distance. Now we also need the intensity. So we know that photovoltaic solar cells have power in the order of kilowatts, and the area is 1 meter squared. So we know that the intensity of the sun reaching the Earth is kilowatts per meter squared, because we know that a photovoltaic cell will collect this energy and make it into electricity. So we know what's the power per surface. This means that according to this formula, conservation of energy and some simple trigonometry, this means that what happens on Earth means it's multiplied by a factor of 200 to the second power is the power emitted by the sun per unit surface. So that's the power of the sun. And then we know that this radiation is visible. We can see it with light, with our eyes. It's light, that radiation is the light that we see coming from the sun. So we know that the visible light has a wavelength of 10 to the minus 6 plus or minus. So that must be the maximum of the wavelength. And then the speed of light is 3 times 10 to the 8. You put everything together, you get that constant to have this value. Well, the exact number that you measure in the lab is this value. So if you do an experiment, you can measure this. If you do this thought process, let's get units right, let's observe what's around us. Can we get the units right based on this observation? Then these two numbers are the same. So this means you're on to something. That is called a 21st century skill. You have to have the units right. It doesn't make any sense. Let's be logical here. Get them right from some simple observations. And if this agrees with your experiment, at least in the order of magnitude, you don't get the coefficient correct. You don't expect that. But this order of magnitude is 10 to the minus 34. Why not 1? Right? You get that right by this argument. And then another argument is, what if this constant doesn't exist? Repeat the same process without the h bar. And then you get an infinite integral, just from the units. So this is indeed what classical theory predicted, which means that the sun will radiate infinite energy just because it has a temperature, and we should not exist. So quantum physics does make a difference. And the reason why Planck, so this guy here, postulated a function that he can restore the units by just putting a dimensionless quantity into some mysterious function. He fitted this function to experiments based on the fact that the behavior does not depend on the object, as we said, just on the temperature. So it's called a universal function. And this is called the Bose-Einstein distribution function, that is the basis of new phenomena like Bose-Einstein condensation and so on, and that makes the integral finite. All right, anything peculiar in this picture? Just a bunch of men, right? Middle-aged to late. All right, well, women, in fact, were among the pioneers in all of this, right? It just was one woman there, Madame Curie, among many men, right? Fortunately, this is not the situation anymore, but this means that women were pioneers in all of this. So it is not correct to say that women don't go in STEM. Let's do some parting thoughts here, and I conclude. So the first thing, develop unique human skills to avoid being disrupted by a robot, meaning a robot can do calculations, but these calculations can be garbage in, garbage out. Robot doesn't know how to think. It doesn't have human skills. Only you have human skills. Develop them. Second, become digitally fluent and not digitally literate. It's no longer enough to know how to program. You have to be able to solve problems with programming. If you learn a language, don't just learn how to read and write. Learn how to write a poem or a novel with that language. Don't chase credentials or degrees just because they are marketable today. Remember that most of the jobs of tomorrow have not been invented yet. So if you just keep collecting credentials and degrees, you will never learn any 21st century skills. The robot will get you. Start with your passion, think differently. Don't think what I'm gonna do in my life. Don't think about your major and all of that. Start with your passion. Why? Why would my life be important? Focus on the skills that will empower you to pursue your passion, and then build a CV that will get you a job that allows you to put food on the table to be able to serve your passion. And then learn how to learn early enough. All the technologies you will need to solve the problems that you really care about because of your passion have not been invented yet. So learn how to learn in order to learn them when they come around. And finally, and most importantly, don't be constrained by the past when the opportunities of the future are boundless. Thank you.
Just want to thank Professor Parakis for this fascinating talk today and for being with us. Do we have any questions from the attendees for Professor Parakis?
I just have a couple of comments. The first part was wonderful, the middle part was wonderful, and this last part was wonderful. More people need to hear, especially the first part and this last part. So I've just got a couple of examples that you might be interested in. I understand from some people, when the space program was in full tilt, Huntsville had a lot of engineers that worked in the space program, and then the space program, was reduced after the Apollo and the moon shots. And so a lot of those engineers in Huntsville were out of jobs. And so a lot of them then found jobs in other fields. And I heard one of them say that he became a teacher, like a high school teacher, and loved it. It was really what he should have been doing as his career. But when he was coming along, engineering was the thing. And so he went into engineering. But then he found out that his life really was in teaching. So I found that to be true related to some of what you're saying. And the other thing that I've come across that I might be interested in is that in the early, in the mainframe computer days, in the early 1980s, I have a whole file folder of articles indicating that the best computer programmers are female English majors. Okay. As a matter of fact, there were people in some of the big companies in Birmingham like Sonat, and they would come to UAB and recruit female English majors for their COBOL programmers, because they said in 6 weeks, we can give them all they need to know about COBOL programming. We need their ways of thinking and their approach to things. And the female, because a male tries to jump to the end, in general, tries to jump to the end conclusion too quickly. A female generally will work through a problem step by step. And they said English majors because English is a very structured discipline. If you're talking about grammar, it's very structured. If you're talking about poetry or literature, very structured, beginning of a novel, middle, end. And so they hired female English majors, UAB. So I found that really tracking to what you were saying at the beginning is you can pick up the technical skills oftentimes, but you need that type of thinking, that type of liberal arts. We called it liberal arts education when I was coming along. You need that general liberal arts education to underpin and to really help you approach everything in life, including your work. So it's very helpful. So thank you very much.
Yes, and all I'm trying to say here is that that's how you do research in a very technical field like physics. That's how you do it. Ada Lovelace, I believe was her name, right? That was the first programmer, and that was a female, right? Back in the early centuries, right? So she had the skills that were required, and she had the interest to put these skills to this, right? Now, the main thing here, and that's how you need to think about it, is how you're going to impact life on this planet while you're still around. And this can be through teaching, it can be through others, right? If that's what you feel is important for you, or it can be doing very technical things. And these things may change through your life. You may decide that you will have an impact first as a teacher and then as an engineer. All of that is part of how life is, right? And with the fourth industrial revolution, that is now the norm and not the exception. And we have to understand that and change our mindset. So the most important thing for me that a student should learn is they have to approach life with the right mindset that is in tune with reality and not with the past.
You bring up another thing that I've heard in the past. You may not remember specifically what you learned from a elementary school teacher or high school teacher, but you oftentimes remember what that teacher meant to you and how that teacher helped you out. You don't know what you learned from them necessarily, but I think that's the important thing is that what a teacher and a professor is to a person makes a big difference.
Exactly. And the same applies, for example, for the chair of the department or the dean, right? So if my faculty get the Nobel Prize, I get the Nobel Prize as well, because I created the right environment for my faculty and I encouraged and mentored and everything for them to be able to succeed. If I get the Nobel Prize, I should go ahead and get it, but not everybody will get a Nobel Prize. So if through your teaching in elementary school, you inspired or prepared somebody with the right skills and the right mindset for them to get the Nobel Prize later, both of you are Nobel Prize winners, even if you were his elementary or her elementary school teacher.
Do we have other questions from the attendees? Yeah, I think it's really an exciting opportunity for students. Just this concept that we're entering this fourth industrial revolution and that we have now kind of on the precipice of the applications of quantum computing and quantum science. I know that, you know, even a decade or two, these were research topics, and now we're starting to see companies take these applications and run with them. So I don't know, maybe if you could talk about the potential for growth there for students so they can kind of put it in perspective.
Right. So here, you know, students that don't come in with the right mindset will not do well.
Yeah.
Right. So this is important. This is not in the past. It happened in the past as well. But the way that the economy and technology has evolved, this is really critical for students' well-being. You think you go to a major just because of the name or the title of the major, that it is marketable. And this is correct today, but not tomorrow. It's like Amazon chasing. eToys is bankrupt and Amazon is around. So that's what I have to say. Now, in terms of research, so things I didn't talk about was the reverse. So machine learning and artificial intelligence will be important because they have the capacity to solve problems that will not be solved before. And these problems right now include very trivial problems that make people money. The hard problems, that we face as a society will only be solved with new capacity that we didn't have yet. Because if we were able to solve them that easily, we would have solved them before. So what is happening now is you're basically getting accustomed with these techniques, and you're developing these techniques in order to do something. And that something has to do with money, because that will get you a job that will allow you to develop these techniques, because you need to bring food to the table. So if your passion is to use these techniques to solve problems for humanity, you may still go through a job of using these techniques for a company that sells products, because that's the only way to develop these techniques. So, and then later on again, you go back to your passion, get out of the job and move to your next job that may be to the next level. Okay. Now, for example, if you want to take a grand challenge problem, and I will leave things like the environment and things like that, let's take precision medicine. So precision medicine is supposed to be the #1 challenge for medicine right now. How to use computation in order to cure patients. So in order to achieve that, you go to the genome, you decode the genome, and then you use that information, that big data, to come up with a cure to the patient, for example, for cancer and all of that. That's the idea behind precision medicine. Nobody has really cured any patient yet using a computer. No, not because this is a really bad idea, but if we stick to a marketable degree, this means that anybody that wants to pursue precision medicine, that's useless. Because surely it doesn't make you any money today, right? Now, how do you pursue precision medicine? You're going to use artificial intelligence and machine learning for that, for sure. The question is how and what to do with that information. And remember, now you have to cure a patient. So this is no longer just physics, where if I screw up, I'll burn something, it will be expensive, but that's all I'm going to do. You will kill a patient, right? The patient is your advanced material. A patient is made of electrons and protons, just like the rest of all materials. And you try to understand that material based on computation. But you do the same thing in physics. And you do it, if you're going to solve a material science problem, you're going to do it. So I had these slides, which of course, I didn't get to. So if you look at the material nowadays, this material looks complicated and you need to control it. So how do you do that? Computation is really important, including machine learning and artificial intelligence. So if I learn how to manipulate the heart, for example, and cure arrhythmia, let's say, by treating the heart as a material and going in very precisely in a computationally well-defined way and knowing where to strike on the heart, then maybe I will do precision medicine. Or if I understand how the neurons in my brain work all together, not one by one, they work all together. So they're in an entangled state. They all work together just like the qubits. Now, whether this is quantum mechanical or not is another story. It doesn't have to be quantum mechanical, but we don't have a clue what it is. So there, again, if I can use quantum physics and the skills I developed as quantum physicist in my undergraduate or my graduate degree by solving materials that are a little bit harder than the simple materials we have been solving in both engineering, in chemistry, and biology so far, right? And solve them in a non-empirical way. Biology has very interesting materials, but it doesn't have yet a method to do that systematically like physics has, because it's too early. This means that a method will come and that will be really exciting and important and transformative, but we're not there yet. So rather than working for Amazon, for example, which is a very good choice, you can also work with your PhD in physics to develop these skills and then go work for a company with these skills. And then go back to biology when the time is right for precision medicine and apply them, right? And by the way, big data was the way that the Higgs boson was discovered in the CERN experiment. The data, if you look at the data, is just a bunch of noise with some small bump there. You have to use machine learning and big data methods in order to understand whether this little bump is important or not. And that's how the Higgs boson was discovered. So if I develop a generation of data scientists that can take data science to precision medicine because they were trained in a non-trivial problem at CERN. That's exactly the definition of the fourth industrial revolution and how you should think about your degrees and your skills and your education, lifelong learning, and the figure is, the one that I showed you in the beginning, where basically you go through life in this engaged, learn, recondition mode, going back and forth, and not in the way that you were going through life before, just because of the nature of the problems you have to solve today and the nature of the economy.
Dr. Parakis, there's a question in the chat from Colin who asks, as we transition to a borderless digital age, how does this affect the role of the nation state?
So again, you're asking hard questions. And again, if I look at this slide, 65% of the jobs do not exist yet, right? The ones that you will be doing, right? So this means that how things will evolve in the future, we have made life very, very complicated and complex. That's how it was from the beginning, but we had this illusion for many decades that it was simple. So the point is, what we want is a better life. So is this your passion? Do you want to make life better on this planet? It doesn't matter how you're going to get there. What matters is that you do get there. So then you go through life, right? So there's going to be an evolution of things. So every time there's an evolution, you have to think, is this evolution to the better or to the worse, in your opinion? And what are your skills that allow you to answer that question and make that question better, right? Then out of this collective effect, this synergistic effect of the entire planet, the entire 8 billion, whatever people live on this planet right now, if all of these could work collectively, everybody comes in with their own skills and their own ideas, what is important. Then out of this collective phenomenon, just like in physics, you get order out. You will get order. So what will that order be? I can't predict that, just like I can't predict what is the job you will be doing 20 years from now. I just can't. What I can predict is that if I have the will to put my skills, which means I have skills in the first place, to put them in good use, to make whatever the jobs will be and whatever the new nations will be or whatever, whether they're old or new, they have to be better. So if with the old structure, I can make humanity better, then that's the good structure, because that gets the job done of what will have the impact in the end. If we can all decide, all 8 billion of us, what is the end goal? And all of us have skills that we bring to the table, and everybody tries something from their own angle, even if it's small, then eventually something will come out, but I can't predict what that will be, just because that's how life works.
Thank you so much. Again, I just want to thank Professor Parakis for being here with us today and giving students an opportunity to hear about quantum mechanics and the future of work and the fourth industrial revolution and all of these really important skills that are great for jobs and also for lifelong learning. So I appreciate it. So please, we'll be back for a talk in late November or early December for our last talk for the semester. So please join us for our Sigma Xi talk. We will send out announcements, and I hope everybody has a wonderful day.
Thank you.
Thank you.